Lesson 7.3, Multivariable Linear Systems and Row Operations. In this lesson, we're going to talk about many new strategies that we haven't talked about in the past. Okay, they're not really difficult, but they are time-consuming. Okay. So what we're going to focus on in this lesson: triangular forms of linear systems, Gaussian elimination, elementary row operations in row echelon form, reduced row echelon form, solving systems with inverse matrices, and then discuss a few applications of these types of problems. First, we need to discuss some operations that will produce equivalent systems of linear equations. Okay, so we can use these strategies to rewrite the equations in a different form that will allow us to work with them more easily. Okay, so the first thing, we can interchange any two equations of the system. So if I want to switch the order of the first and second equations, I can do that. Second thing, we can multiply or divide one of the equations by any non-zero real number. Okay, we know that if we multiply any side in an equation by the same value, as long as we're doing that to both sides of the equation, that's alright. And the third thing, we can add a multiple of one equation to any other equation in the system. Now we're going to talk about row echelon form of a matrix. So a matrix is in row echelon form if all of these three conditions are satisfied. First, rows consisting entirely of zeros. If we have that occurring, those are going to be at the bottom of the matrix. Second thing, the first entry in any row with non-zero entries must be a 1. And the third condition, the column subscript of the leading 1 entries increases as the row subscript increases. The process of using these row operations to rewrite a matrix in row echelon form is called Gaussian elimination. Okay, that's named after Carl Gauss, who you could see the picture of on the front slide when we started this lesson. So we're just going to refer to it as row echelon form. The process of getting it into row echelon form is called Gaussian elimination. Okay, so now we're going to go through an example where these three conditions will hopefully make a little more sense. So below we have two different matrices. Okay, the one on the left, this one would not satisfy a matrix in row echelon form because if we look at the leading entries in each row, they are not a 1. The leading entry in this row is a 2. The leading non-zero entry in this row is a 3. This row has a leading entry of 1, but all three of the rows need to have a leading entry of 1 in order to be in row echelon form. So this one will not satisfy that condition. If we look at the second matrix, each of our rows has a leading coefficient of 1. Okay, so that condition is met. The third condition we talked about before, the column subscript of the leading 1 entries increases as the row subscript increases. So as we go here from our first row to our second row, we're looking at these values of 1. Okay, each of our leading coefficients in each row must be 1. As our row increases, as we go down, our leading coefficients where they start must go at least 1 unit to the right. So from this first 1 we had in our first row, first column, as we go down 1 row, our leading entry of 1 must go to the right at least 1 column. And that pattern has to continue. Basically, our 1s have to lie within this column, okay, within this main diagonal. All of the other values below, these entries are going to be zeros to the bottom left of those 1 diagonals. If we're trying to rewrite a matrix so that it's in row echelon form, we can perform the following 3 operations to get it into that form. Okay, so first, we can interchange any two rows, what we talked about earlier. Second thing we can do is multiply all elements of a row by a non-zero real number. Or the third thing, we can add a multiple of one row to any other row. So these are the 3 basic operations that we can perform on a matrix to write it in row echelon form. Now we're going to go through an example of writing a matrix in row echelon form. So suppose we have the following system of linear equations. Okay, we have 3 different equations and 3 different variables. If we want to write this system of equations in a matrix, all we have to do is take the coefficients in front of each variable and the constants to do that. So our first row would consist of the numbers 2, 3, -1, and -1. Our second row would be -1, 5, 3, and -10. And our third row would be 3, -1, -6, and 5. So if we're going to create this matrix, all we have to do is take the coefficients in front of each variable and the constant at the end to create this 3x4 matrix. So now if we're going to write this matrix in row echelon form, our goal is to get all of these values to be equal to 1, and all of these values are going to be 0. If we can do that, then this will be in row echelon form, and you'll see why that's beneficial or easier for us to work with. Okay, so we're going to use those three basic operations. We can interchange any rows, we can multiply any row by a non-zero constant, a non-zero real number, or we can multiply a row and add it to another row. Okay, so those are the three basic operations we're going to do to write this matrix in row echelon form. So the first step I'm going to perform to write this in row echelon form is I'm going to, the notation we use, we always construct this arrow to say we're going from one matrix to the next. We're performing that operation. Okay, that yields, we always need that. This R with the subscript of 2, 1, that means we're interchanging rows 1 and 2. Okay, so all I did from the first matrix to the second, I switched row 1 with row 2, which is one of our three operations we can use to write a matrix in row echelon form. And the next step, all I did was take -1 times row 1. Now if we do that, you can see the leading coefficient in row 1, okay, our leading entry is a value of 1, which we need. Okay, now our goal is to get those other values along that diagonal that I talked about before to be a value of 1. Okay, and the next step, now we need to start getting the leading coefficient to be a 1 in the next two rows. So what we're going to do in the next step is multiply -2 times row 1, and then add that quantity to row 2 to create a new row 2. Okay, so we got a lot going on. So what we're doing, if we look at our first entry in our first row, what we're going to do, multiply that by a -2. So we take 1 times -2, get -2, add that to our entry in row 2. So -2 plus 2, now we're going to get a value of 0 in our new row 2 that we're creating. Alright, we're going to do the same thing for the next step. We're going to take -2 times 5, which would give us positive 10, add that to row 2, so 10 plus 3 gets us our 13. We would continue this pattern on for the rest of them. We're taking -2 times -3 to get 6. 6 plus a -1 gets us our 5. Okay, so the reason we're doing that is now if we look at row 2, we have a 0 starting out in that row, which we need. Okay, we need, after that first one, the 2 below it in row 2 and row 3 in column 1, those values have to be 0. We're going to use a similar method in the next part. We're going to take -3 times row 1, add that to row 3 to create a new row 3. Okay, the reason we would do that, if we look at our first column, in the first row we have a coefficient of 1, and the ones below that are all zeros. Okay, that's what we need. The next thing we got to do is get these values to be a 1 and this value to be a 0. Okay, so that's what we're going to work towards doing in the next few parts. In order to get the value of 13 to be a value of 1 in row 2, we're going to multiply row 2 by 1/13. Okay, so we're just going to take row 2, multiply each of those entries by 1/13. Now if we look, both of these are values of 1. We need to get this to be a value of 1 and this to be a value of 0. So we're just about done to getting this in row echelon form. Now in this step we're going to multiply -14 by row 2 and add that to row 3. Yes, we're dealing with fractions, but they're actually going to simplify to something that's alright. So if we do that, now we have all of these values equal to 0, and we just need to get one more value equal to 1 in our main diagonal. Okay, so this last step is probably going to be the easiest of all of them. All we need to do is multiply row 3 by the reciprocal of the leading coefficient of row 3, so negative 31 over 13. We're going to multiply that by the reciprocal, which is negative 13 over 31. And if we do that, now those last two entries in row 3 are both going to be equal to 1. So now along that main diagonal we were referring to, all of those values are 1. Every value below and to the left of that main diagonal is equal to 0. So now this is in row echelon form, and now we're going to talk about why this is beneficial in solving a system of equations. So if we think back to the beginning of this problem, we had this system of equations in three variables, x, y, and z. Our goal is to solve the system, meaning we're trying to find the x, y, z, that ordered triple, where these three equations intersect. Okay, so we took this system of equations, wrote it as a matrix, then we used row operations to rewrite this matrix into row echelon form to make it easier to work with. So now we can take this matrix we have and write it as a system of equations. So we're going to take all these coefficients and write it as an equation. So if we're looking at row 1, that means we have x minus 5y minus 3z equal to 10. Now if we're looking at row 2, our second equation, that would be 0x, so we don't have to write that in there. So we have y plus 5/13 z equal to negative 21 over 13. Now if we're looking at our third equation, we have 0x plus 0y, we don't have to write those values in there, so we have 1z, which is just z, equal to 1. Now we're going to solve for the x, y, and z values. Using the third equation, we already know z is equal to 1, so if we plug that z value into the second equation, we have y plus 5 over 13 equal to negative 21 over 13. So if we would subtract that 5/13 to the other side, we would get y equals negative 21 minus 5 is negative 26 over 13, which is equal to 2, negative 2. So we know z is equal to 1, y is equal to negative 2. Now if we take that third equation, or the first equation up top, x minus 5y minus 3z equal to 10, we can plug these values in to solve for x. So x is going to be equal to negative 5 times negative 2 would be 10. We would subtract that to the other side. So we have 10 minus 10. Negative 3 times a 1. We would add that to the other side, so plus 3. So x would be equal to 3. So our ordered triple, we would get 3, negative 2, and 1. That is the solution to this system of equations. So we took our original system, rewrote it in matrix form, wrote that matrix in row echelon form, which allowed us to have an easier system to solve algebraically. We could take row echelon form a step further and write it in reduced row echelon form. So if we continue to apply elementary row operations to a row echelon form of a matrix, we can obtain a matrix in which every column that has a leading 1 has zeros elsewhere. Okay, this is reduced row echelon form. So say we have a matrix along our main diagonal that we've been talking about. These values are 1. We have the values in our coefficient column. Every other value in the matrix is going to be 0. Okay, so if we think about this in terms of solving for x, y, and z, our first column represents our x values, the second column represents the y values, the third column represents the z values. So now if we set up our equations, in the first row we would have 1x plus 0y plus 0z equal to 4. Well, that just gets us x equals 4. In the second row, we have 0x plus 1y plus 0z equal to 3, so y is equal to 3. In the third row, we have 0x plus 0y plus 1z equal to 7, so z equals 7. So reduced row echelon form, it's going to take a lot more work to get it into that form, but it tells us right away what our x, y, and z values are. Next, we're going to discuss invertible squared linear system. Let A be the coefficient matrix of a system of n linear equations in n variables given by ax equals b, where x is the n by 1 matrix of variables, and b is the n by 1 matrix of numbers on the right-hand side of the equations, are constants, the numbers by themselves. If A inverse exists, then the system of equations has the unique solution where x is equal to A inverse times b, x representing our variable matrix, so this is another way to solve a system of equations. In the next example, solving a system using inverse matrices, so our system of equations is 2x minus 3y equals 0 and 2x minus 2y equals 10. So our matrix represented by A, our coefficient matrix, is 2, negative 3, 2, negative 2, simply the coefficients in front of x and y. Our x matrix, the variable matrix, consists of our two variables, x and y in this case. The B matrix consists of the constants, which are 0 and 10. So our basic equation down below is we're taking matrix A times matrix X, that's equal to matrix B. If we want to get x by itself, we need to multiply the left side by the inverse matrix. So we're taking A inverse times A times X equal to A inverse times B. Important thing to notice here is that A inverse, we're multiplying that on the left-hand side, we're multiplying that to the left side of matrix A, and we're multiplying that A inverse to the left side of matrix B. As a constant rule, we're always going to multiply the inverse matrix on the left side. Remember, in the last lesson you learned the order in which you multiply two matrices does matter. So if you take matrix A times matrix B, that's not always going to be equal to matrix B times the matrix A. So the order in which we multiply, just to keep it consistent, always multiply the inverse matrix on the left-hand side. So this simplifies A inverse times A. We're left with X is equal to the inverse of A times B. Next, we need to find the inverse for matrix A. So in order to find the inverse of matrix A, as long as it exists, is we take 1 divided by the determinant. To find the determinant, we need to multiply 2 times negative 2, gives us negative 4, and then we have to subtract negative 3 times 2, which is negative 6. So we have negative 4 minus a negative 6, negative 4 plus 6, our determinant is a positive 2, that's where that value comes from. Then we have to look at the values along our main diagonal, the 2 and the negative 2. In our inverse, those are going to switch positions. And then we look at the opposite diagonal, the negative 3 and the 2, those are going to switch signs. So now we have a positive 3 and a negative 2. Now we multiply that scalar through to each entry, and our inverse matrix is negative 1, 3 halves, negative 1, and 1. Okay, the inverse exists. Our inverse is always going to exist, remember from the last lesson, as long as the determinant of the matrix is not equal to 0. It was equal to 2 this time, so we know we have an inverse matrix. So now we take that inverse matrix, negative 1, 3 halves, negative 1, 1, and multiply it by matrix B, which was our constants, 0 and 10. Our first matrix is 2 by 2, second matrix is 2 by 1. Inside values are the same order, so this matrix is defined. We can find the product. Our product has the dimensions 2 by 1. So if we multiply these out, negative 1 times 0 is 0. 3 halves times 10 gives us 15. Now we take row 2 times that column. Negative 1 times 0 is 0. 1 times 10 is 10. So this means the solution to this system will be 15, 10. To end this lesson, I'm going to go through an extra example on how we can use those three operations to rewrite a matrix in row echelon form. So suppose we have the system x minus y plus 2z equals negative 3, 2x plus y minus z equals 0, and negative x plus 2y minus 3z equals 7. If we take those coefficients and the constants, we can write the matrix 1, negative 1, 2, negative 3, 2, 1, negative 1, 0, negative 1, 2, negative 3, 7. So we're going to rewrite this in row echelon form. The first thing I'm going to do is multiply row 3 by 2 and add that to row 2. Okay, so what that does, that changes the second row to become 0, 5, negative 7, 14. Next thing we're going to take that matrix, we're going to take row 1 plus row 3, and if we do that, that's going to change row 3 to 0, 1, negative 1, and 4. Okay, after that, we're going to switch rows 2 and 3 around. Okay, so now we have 1, negative 1, 2, negative 3, 0, 1, negative 1, 4, 0, 5, negative 7, 14. So you can already see we're getting close to being in row echelon form. Now we're going to multiply row 2 by negative 5 and add that to row 3. So row 3 becomes 0, 0, negative 2, negative 6. We're going to take that matrix. Now we're going to multiply row 3 by negative 1/2 so we can get that coefficient to be 1. And if we do that operation, now we are in row echelon form. All of the values along that main diagonal are 1. Everything below that and to the left are 0 entries. So we could take this last matrix and rewrite that so we have our 3 equations. We have a new system of equations. X minus y plus 2z equals negative 3, y minus z equals 4, and z equals 3. Okay, so that first part, or the third equation, z equals 3, we already know one of our 3 variables. If we go to the second equation, y minus z equals 4, well, we know z is 3, so y minus 3 equals 4, y must be equal to 7. In the last part, we use that first equation, plug in the values we know for z and y, z equals 3, y equals 7. If we plug those in and simplify, we get x is equal to negative 2. So, our order triple, the solution to this system of equations, would be the order triple negative 2, 7, 3. If you look in your books, this is example 4. And if you look through how they used row operations to solve this system of equations, they use different operations. Okay, so when you're going through this process, there is no one right method to approach it. As long as you're using one of the 3 operations, you're going to come to the right solution. Okay, so the main thing with these problems, it's easy to make a mistake. So work slowly, use the operations. Okay, everybody could have potentially a different method to come up with the solution to the system.